All right, continuing on, we're talking about solving differential equations. If we're given no ordered pair on the solution function, then what we're going to find is called a general solution, and we have to add the plus c on the end. If we have an initial condition, an ordered pair on the original function, it's called an initial value problem. And what we do is we find the general solution for the differential equation, and then we use that ordered pair to figure out the value of c so that our final answer has no plus c in it. So here's example 3. Just notice that if the answer we give, if we can give a particular solution to a differential equation, and the solution we give has a function that is not continuous, we have to say which part of the domain of the function our solution is valid for. So we'll get this. All right, I've been told dy dx is 2 minus secant squared of x, and my solution should pass through the point 0, 3. So I'm going to think of antiderivatives in my head. So I think y is going to equal, the antiderivative of 2 is 2x, minus the antiderivative of secant squared of x is tangent x, plus a constant. And now I'm going to use my ordered pair to figure out the value of c. So this is sort of a side step. I'm going to plug 3 in here. That's going to be 2 times 0 minus the tangent of 0 plus a constant. So 3 is equal to 0 minus tangent of 0 is 0 plus a constant, which tells me that c equals 3. So now I'm going to come back to my general solution, and I know what c is now, so I don't have a general solution. I have a particular solution if I write y equals 2x minus tangent x plus 3. So this is a particular solution. There's no plus c on the end, which is what makes it different from example 1. And I notice that tangent is not a continuous function. Tangent has vertical asymptotes at pi over 2 plus k pi. So I have to think about the tangent graph, which is why we made that function booklet at the beginning of the year. Here's tangent. And what I care about is what the tangent graph looks like near where x equals 0, because x equals 0 is the x-coordinate in the ordered pair I know about my function. So this is the tangent function. And the tangent function is continuous near 0, and the piece of the tangent function that goes through the plate that contains x equals 0 is valid between x equals negative pi over 2, which is this asymptote, and x equals positive pi over 2, which is the equation for this asymptote. So I would say that this is my answer, y equals 2x minus tangent x plus 3, and it's valid for x's between negative pi over 2 and pi over 2. And here's the return of the most important example in chapter 5. Notice that one way, it might feel like cheating, it's not really cheating, is different than finding an answer that doesn't contain an integral. But one way to find the solution to a differential equation is to write your function using an integral. So if I know that f prime of x is equal to e to the negative x squared, and I know an initial condition, so f of 7 is equal to 3, then I can write an expression for f of x. Now, I don't know an antiderivative for e to the negative x squared off the top of my head. In fact, nobody does. There isn't a function in the more regular sense of a function whose derivative is e to the negative x squared. But I can write my answer using an integral. So this is going to be the integral from some constant to x of e to the negative, pick a different letter, q squared dq. You could have picked anything except x. Now, no matter what I do with the rest of my function, its derivative will be f prime of x, so e to the negative x squared, as long as that box at the bottom I fill in with a constant. Well, the question is, what constant should I fill in so that f of 7 will be 3? I'm going to fill in 7 as the lower limit, and I'm going to add a 3 out here. Notice that's a plus sign, not a t, so that's 3 plus the integral from 7 to x of e to the negative q squared d cubed.